There are a lot of questions about Oumuamua and space that will remain unanswered unless we're able to act more quickly.
Ever since its discovery in 2017, Oumuamua, the first confirmed interstellar object to visit our solar system, has been captivating scientists. Its unusual nature and mysterious origins have sparked countless studies and theories, making it a landmark discovery in our understanding of the universe. Oumuamua's story began on October 19, 2017, when astronomers in Hawaii, using the Pan-STARRS 1 telescope, designed to spot near-Earth objects, stumbled upon something unexpected. Robert Werrick, a researcher at the University of Hawaii, noticed the object while analyzing data from the telescope. Unlike anything else in our solar system, Oumuamua didn't resemble typical asteroids or comets. News of the discovery spread quickly, and astronomers worldwide trained their instruments on the object. Their observations confirmed it wasn't bound to the Sun by gravity, revealing its interstellar origin. The object was then named Oumuamua, a Hawaiian word chosen by the Pan-STARRS 1 team with the help of language experts. It translates to a messenger from afar arriving first, reflecting its unique status as the first known visitor from another star system. The naming of Oumuamua held significance beyond the object itself. It acknowledged the contribution of Hawaii and its people to astronomical discoveries. While initially classified as an asteroid due to its lack of a visible coma or tail, Oumuamua's unexpected acceleration as it left our solar system threw scientists a curveball. This behavior is characteristic of comets, which expel gas and dust for propulsion, but Oumuamua displayed none of the usual signs. One theory suggests Oumuamua might still be outgassing, but invisibly. The release of a small amount of gas or dust undetectable by telescopes could explain the acceleration, making it a new type of comet without the usual visual cues. However, Harvard astrophysicist Avi Loeb took things a step further with a more controversial theory. Oumuamua could be an artificial object, possibly a light sail from an advanced alien civilization. He cites its unusual shape, shiny surface, and unexpected acceleration as evidence against a natural origin. Loeb suggests Oumuamua's high-speed, sun-grazing trajectory and sudden acceleration could be explained if it were a probe or light sail, a thin sheet that uses solar radiation for propulsion. While captivating, this theory is highly speculative and lacks broad scientific acceptance. Scientists have proposed several alternative explanations within the realm of natural phenomena. One theory suggests it could be a fragment from a disrupted planet or other celestial body, which could explain its unusual shape. Another interesting theory proposes it as a hydrogen iceberg, composed of molecular hydrogen ice. As it neared the Sun, the ice sublimated, transforming directly from solid to gas and providing thrust without a visible tail. However, the feasibility of such an object surviving interstellar travel remains debated. Some researchers also believe it could represent a new class of interstellar object, formed through unknown processes. Its characteristics might be typical for objects ejected from other star systems, potentially leading to the discovery of more similar objects in the future. Oumuamua's extraordinary shape, far more elongated than any known object in our solar system, has captivated scientists. Estimates suggest it's roughly 800 meters long and 80 meters wide, with a remarkable 10-to-1 aspect ratio. Determining the exact shape is challenging due to limitations in observing such a distant object. Unlike most solar system objects, Oumuamua exhibits a tumbling motion, hinting at a possibly violent past. It also shows a non-gravitational acceleration as it moves away from the Sun, a phenomenon not fully explained by the Sun's gravity. The dark reddish surface, similar to some outer solar system objects, suggests the presence of organic molecules. This, along with its color and other characteristics, points towards a composition similar to comets and objects beyond Neptune in our solar system. The long journey and exposure to cosmic rays could explain the darkened surface, potentially masking its original composition. While the investigation continues, these unique characteristics offer valuable clues in unraveling the mystery of its origins. Oumuamua's journey through space is estimated to have spanned billions of years, leaving its mark on its surface. The object's dark reddish color is a telltale sign of prolonged bombardment by cosmic rays, which can alter the chemistry of interstellar objects over time, creating complex organic molecules. This long exposure to the harsh environment of space suggests a lengthy voyage through the vast interstellar medium. Remarkably, the frigid temperatures and near-vacuum conditions of interstellar space can act as a natural preservative. Unlike objects within our solar system exposed to solar radiation and atmospheric wear and tear, Oumuamua's surface may have remained largely unchanged since its ejection, offering a potential glimpse into its original state. Scientists are piecing together the puzzle of Oumuamua's path using a combination of observations and simulations. They analyze data on the object's position, speed, and acceleration during its passage through our solar system, factoring in the gravitational influences of the Sun, planets, and other celestial bodies. One key concept is the gravitational slingshot effect, where an object gains speed by passing close to a massive body. By calculating the cumulative effect of such encounters during its journey through our solar system and backtracking through time, scientists can chart a possible course for Oumuamua's arrival. Several studies have attempted to identify stars or systems Oumuamua might have encountered during its travels. Some possibilities include young star clusters and even specific stars like HIP 3757 and HD 292249, which had close approaches to Oumuamua's trajectory millions of years ago. However, pinpointing the exact origin remains a challenge. Uncertainties in Oumuamua's velocity and the dynamic nature of our galaxy, where stars are constantly moving, make it difficult to trace its path with precision. Any non-gravitational acceleration, like that potentially caused by outgassing, further complicates the calculations. As Oumuamua ventures through interstellar space, it interacts with the interstellar medium, a sparse collection of gas, dust, and charged particles. While seemingly insignificant, this medium can exert subtle forces on objects over immense timescales, potentially altering their trajectories. These subtle influences, like drag from dust or gravitational tugs from unseen matter, add another layer of complexity to reconstructing Oumuamua's long journey. Despite the challenges, Oumuamua's interstellar origin, confirmed by its unique trajectory, makes it a valuable visitor. It offers a rare opportunity to study material from another star system, providing insights into the composition and formation of objects beyond our solar system. Ever since its discovery in 2017, analyzing its trajectory and speed has been crucial to understanding its path and future. Unlike planets and most objects in our solar system that follow closed elliptical orbits, Oumuamua is on a hyperbolic trajectory, an open path taking it permanently out of our system. After a close encounter with the Sun, it gained enough speed, roughly 26 kilometers per second, which is about 58,000 miles per hour, to escape the Sun's gravitational pull. Currently, it's journeying towards the constellation Pegasus and won't be returning anytime soon, so we think. As an interstellar object, Oumuamua's journey through our solar system was a brief stopover. Its immense speed ensures it won't be captured by the Sun's gravity, meaning no return visits are possible. Extensive calculations confirm this one-way trip, with Oumuamua destined to become a permanent wanderer among the stars in the Milky Way galaxy. Scientists have meticulously analyzed Oumuamua's trajectory. Its hyperbolic path, unlike the closed orbits of planets, signifies its interstellar origins and independence from the Sun's gravitational influence. Furthermore, its speed and the direction it entered the solar system, originating near the constellation Lyra, couldn't be explained solely by interactions within our system. While the object's age and the vast distances involved make pinpointing its exact source challenging, tracing its entry point provides valuable clues about its potential home. So will Oumuamua return? Not in our lifetime, but maybe another one. Understanding Oumuamua's trajectory unveils its journey as a one-time encounter and underscores its status as a permanent ambassador from another star system, offering a glimpse into the wonders beyond our solar neighborhood.
And on this record are a sampling of pictures, sounds, greetings, and an hour and a half of exquisite music.
The Voyager Golden Records, launched aboard the Voyager spacecrafts in 1977, serve as a cosmic message in a bottle, a way to introduce humanity to potential extraterrestrial intelligences that might discover them in the far reaches of space. Imagining what could happen if aliens found the Golden Records opens up a realm of intriguing theories and ideas. Imagine, if you will, the Voyager Golden Records floating through the vast expanse of space, carrying the essence of human civilization on their surfaces. These records, A blend of music, language, and images were sent into the cosmos with the hope that one day they might be found by beings not of this earth. It's a thought that tickles the imagination and raises questions about how we might be perceived by advanced extraterrestrial civilizations. Would they see us as potential allies, or would the contents of these records cast humanity in a more threatening light? The technology behind the Voyager Golden Records is a marvel of the late 20th century. They contain analog information that showcases Earth's diverse cultures through sound and imagery. The very method of encoding analog might seem quaint or even rudimentary to us now, but to an alien civilization, it could represent a critical insight into our technological capabilities at the time of the spacecraft's launch. It's a bit like when European explorers first encountered indigenous peoples across the globe. The technological disparities led to significant misunderstandings about the complexities of these societies. In a similar vein, extraterrestrials finding the Voyager records might misinterpret our technological level, either underestimating or overestimating us based on their own advancements. Beyond our gadgets and gizmos, the Golden Records offer a window into the human soul. The diversity of languages and expressions of art and science might provide these hypothetical beings with a snapshot of our social structures and behaviors. Yet the selectivity and brevity of this content could lead to skewed interpretations. It's conceivable that extraterrestrials could study these records to understand our propensities for conflict and cooperation. Our history is rife with both, from the intense rivalries and technological races of the Cold War era, which saw the launch of the Voyager spacecraft, to moments of profound cooperation, such as the Apollo-Soyuz test project. How extraterrestrials interpret these dichotomies, our capacity for both aggression and unity, could influence their assessment of humanity. Another angle of interest might be Earth's natural resources, as indirectly depicted through the images and sounds of nature captured on the records. The abundance of water, the diversity of our biosphere, and the variety of climates could make our planet an attractive target for exploration, or perhaps more worryingly, for resource extraction. This aspect mirrors the human history of exploration and colonization, driven by the quest for resources, a reminder of the potential consequences of such encounters. The discovery of the Voyager Golden Records could lead extraterrestrial civilizations to weigh the benefits of peaceful interaction against the risks of hostility. Considering the vast distances involved in interstellar travel, any civilization capable of reaching the Voyager spacecraft and interpreting its contents would likely have technology far superior to our own. This disparity might incline them towards peaceful engagement, preferring the mutual benefits of cultural exchange or technological collaboration over the uncertainties of conflict. The idea that the Voyager Golden Records might one day spark the first contact with an alien civilization is nothing short of exhilarating. Picture this. Somewhere in the vast expanse of space, an alien civilization stumbles upon these records, a cosmic greeting card from Earth, and decides to reach back out to us. The conversation around protocols for extraterrestrial contact is already underway, though consensus on the exact procedures remains elusive. The SETI Institute has laid out guidelines that include verifying the authenticity of any signal received, managing how information is shared to prevent public panic, and ensuring a coordinated response. Similarly, the International Academy of Astronautics has crafted protocols emphasizing international cooperation and the transparent sharing of data. These guidelines are primarily geared towards signals detected from afar, not the physical encounter implied by the discovery of the Voyager records. The distinction is crucial because the latter scenario suggests that the extraterrestrial beings have the means to traverse the cosmos, potentially bringing them directly to our doorstep. Such a prospect raises the stakes significantly, bringing into focus not just how we communicate but also the intentions and capabilities of our visitors. Effective communication with extraterrestrials presents a formidable challenge, necessitating breakthroughs in how we understand and translate fundamentally different ways of sensing, thinking, and expressing. The records carry a snapshot of human languages and cultures, but the task of conveying the complexity of our societal norms or ethical values to beings from another world would be daunting. Experts in linguistics and communication theory have posited that mathematics, music, or even visual symbols might serve as rudimentary bridges between our worlds, a starting point for building a shared language. This situation isn't without precedent. though any historical parallels such as the encounters between differing human cultures here on Earth only offer a rough guide. After all, the gap in biology, perception, and societal development between us and extraterrestrial beings is likely to be vast, introducing complexities we can scarcely imagine. The necessity for a unified global response to extraterrestrial contact underscores the importance of international collaboration. The event of an alien civilization finding the Voyager records and reaching out would undoubtedly be a global phenomenon, demanding a level of cooperation and coordination beyond anything we've experienced. While organizations like the United Nations Office for Outer Space Affairs provide a framework for managing outer space affairs, they would need to be significantly empowered to handle the nuances of interstellar diplomacy. Ethical considerations also come to the forefront in discussions of first contact. The encounter poses deep questions about humanity's place in the cosmos, the rights and dignities of other sentient beings, and our responsibilities as a potentially technologically lesser civilization. Philosophers and ethicists advocate for a cosmic perspective that values all forms of sentience, urging us to approach such contact with a mindset of peace, respect, and an openness to the profound moral and social implications it entails. The history of European colonization, with its stark lessons on the dangers of unequal power dynamics, serves as a cautionary tale, reminding us of the importance of ethical preparedness and a commitment to equity and respect in all our interactions, earthly or otherwise. With greetings in 55 languages, sounds from nature, music from various cultures, and a visual depiction of life on Earth, the records are a rich representation of humanity. Yet this diversity and complexity pose a significant challenge to any extraterrestrial beings trying to decipher them. It's like trying to understand a story when you only know a few words of the language it's told in. Enter the universal language of mathematics, often considered a fundamental structure that underpins the universe. This idea suggests that mathematical concepts, from the simple to the complex, are constant and immutable, cutting across cultural and linguistic barriers. For instance, the Pioneer plaque, which preceded the Voyager records, used the hyperfine transition of hydrogen as a basic unit of time, banking on the assumption that any advanced civilization would be familiar with hydrogen. Similarly, the binary numbering system encoded on the Voyager record was chosen for its simplicity and universality, offering a stark contrast to the complexity of human languages, which are deeply tied to our experiences and cultures. But the beacon of hope that mathematics provides does not fully illuminate the path to mutual understanding. The way extraterrestrials might interpret mathematical information, or the concept of encoding itself, remains an open question. Some theorists speculate that alien civilizations could have developed entirely different sensory and cognitive systems, influencing how they perceive and interpret information. Imagine a civilization that evolved in darkness, using vibrations or electromagnetic fields to communicate, encountering the visual and auditory information on the Voyager records. Beyond mathematics, decoding the records might require extraterrestrials to grasp symbols or contextual clues embedded within, not just the data, but also the meta-information about how it's organized and presented. The records include a diagram showing Earth's location based on 14 pulsars, using universal constants to convey information. However, understanding these symbols would require a leap in understanding celestial navigation and mapping, assuming shared knowledge that might not exist.
But I think the development of full artificial intelligence could spell the end of the human race. We can and must use our curiosity and intelligence to look to the stars.
Stephen Hawking, a renowned theoretical physicist, wasn't just known for his groundbreaking discoveries in cosmology and black holes. He also shared his concerns about the future of humanity, touching on various topics with his characteristic scientific insights and their potential impact on society. Here are some of the fears and concerns he expressed for the future of humans. One of Hawking's concerns was the threat of asteroid impacts on Earth. This isn't just science fiction, it's a real possibility that has happened before and could occur again if we don't take preventative measures. Asteroids are rocky remnants from the formation of our solar system, and while most are found in the asteroid belt between Mars and Jupiter, some have orbits that bring them closer to Earth, making them near-Earth objects. The most famous historical example of an asteroid impact is the Chicxulub impact, estimated to have occurred 66 million years ago. This colossal event is widely believed to have caused the mass extinction that wiped out the dinosaurs and roughly 75% of Earth's species at the time. The impact created a crater roughly 150 kilometers wide in what is now the Yucatan Peninsula in Mexico, and the environmental changes it triggered, including widespread fires, tsunamis, and a nuclear winter caused by dust blocking out the sun, showcase the potential catastrophic consequences of large asteroid impacts. While most near-Earth objects are small and harmless, burning up in the Earth's atmosphere, larger ones could cause significant damage upon collision. The level of threat depends on the size of the asteroid, with larger ones potentially causing regional or even global disasters. Thankfully, efforts are underway to protect Earth from asteroid impacts. The first step is detection and tracking. Several programs like NASA's Near-Earth Object Observations program are dedicated to discovering and monitoring objects. These programs use ground-based telescopes and space-based sensors to track the trajectories of asteroids that could potentially impact Earth. Fortunately, scientists haven't just identified the threat, they're also exploring ways to deflect or mitigate potentially catastrophic asteroid impacts. One method involves a spacecraft essentially playing cosmic bumper cars. The kinetic impactor technique involves launching a spacecraft to deliberately crash into an asteroid, ever so slightly altering its trajectory and nudging it away from Earth. An example of this technique being tested is NASA's DART mission, aiming to practice this method on a smaller asteroid. Another approach is the gravity tractor method. This strategy involves a spacecraft slowly flying alongside an asteroid for a long time, using its own gravity to gradually pull the asteroid off course. Nuclear explosions are a more controversial option. The idea isn't to blow the asteroid to smithereens, which could create multiple smaller threats, but to use a precisely detonated nuclear explosion near the asteroid to create a powerful push, altering its course. The good news is that we're not facing this challenge alone. The international community recognizes the global threat posed by asteroids. The United Nations has established organizations like the International Asteroid Warning Network to share information about potential threats, and the Space Mission Planning Advisory Group to coordinate international efforts in deflecting dangerous asteroids. For example, an asteroid named Apophis gained notoriety for its potential to hit Earth in 2029 or 2036. Thankfully, further observations have ruled out any impact threat from Apophis for at least the next 100 years. While not an immediate danger, close encounters like these offer valuable opportunities for scientists to refine their tracking and deflection techniques, ensuring we're better prepared for any future threats that may arise. The search for extraterrestrial life is in full swing, with scientists using telescopes to listen for possible signals from distant civilizations. But amidst this excitement, Stephen Hawking offered a word of caution regarding the potential dangers of contacting aliens. His concerns, while thought-provoking, are part of a larger conversation about the possible consequences of encountering life beyond Earth. SETI projects aim to detect signs of intelligent life by searching for radio signals that could be of artificial origin. Additionally, the Messaging to Extraterrestrial Intelligence initiative seeks to send messages into space in the hopes of establishing contact. However, Hawking's viewpoint urges us to consider the potential risks involved. His perspective is influenced by the precautionary principle, which essentially states that when the potential consequences of an action are unknown, it's best to err on the side of caution. Applied to contacting aliens, this principle implies that without understanding their intentions or capabilities, we should proceed with caution. One of Hawking's concerns is the possibility of encountering a civilization far more advanced than ours. He points to the concept of the technological singularity, a hypothetical point where technological advancement becomes rapid and unpredictable. Extraterrestrial civilizations that have reached this stage might possess unimaginable technologies, potentially including methods of interstellar travel, advanced energy manipulation, or even control over the fabric of spacetime. Furthermore, Hawking mentions von Neumann probes, self-replicating spacecraft theorized by some as a means of interstellar exploration. If such probes are designed to acquire resources, Earth could become an unwitting target, highlighting the potential dangers of resource depletion in space exploration. Beyond technological risks, Hawking also raises concerns about unique type of consequence. He draws a parallel to the Columbian Exchange, a historical period where the introduction of foreign plants, animals had devastating effects on indigenous populations in the Americas. An encounter with aliens could lead to similarly unforeseen and potentially catastrophic consequences. The theory of directed panspermia adds another layer of complexity. This theory suggests that life on Earth may have been deliberately seeded by an advanced civilization. While speculative, it raises the possibility of contamination in both directions, with not only Earth's biosphere being at risk from alien organisms, but also the potential for us to unintentionally harm extraterrestrial ecosystems. Hawking's cautionary words, while not a call to abandon the search for extraterrestrial life, encourage us to approach potential contact with an open mind, but also with a healthy dose of prudence and awareness of the potential risks involved. Our quest to find out if we're alone in the universe has sparked a multitude of fascinating theories and concepts. Stephen Hawking had some interesting ones. Here are a few that attempt to answer the age-old question, are we truly alone? The zoo hypothesis takes a hopeful approach, suggesting that advanced alien civilizations might be observing us, like specimens in a cosmic zoo. This theory implies a sense of responsibility and non-interference on their part, perhaps similar to the concept of a prime directive in science fiction. However, the zoo hypothesis also presents challenges for the search for extraterrestrial intelligence. If aliens are actively hiding or avoiding contact, SETI might need to go beyond just searching for signals. They might need to look for subtler signs like evidence of observation or manipulation from these advanced beings. This concept ties into the idea of the anthropic shadow, which suggests our observations about the universe are inherently biased. We might only see what allows for our own existence. If civilizations readily expose themselves or interact carelessly, they might not survive long enough to be observed, making the silence seem deafening. On the flip side, the dark forest theory paints a much bleaker picture. It imagines the cosmos as a dark and dangerous place where every civilization acts like a silent hunter, fearing to reveal their location to potential threats. This theory, inspired by science fiction, is based on the idea of cosmic sociology, exploring how civilizations might interact based on survival and risk. The dark forest theory delves into the chilling concept of cosmic loneliness. The vast and silent universe, it suggests, could be a result of civilizations' fear of annihilation, driving them to hide rather than seek contact. This theory also introduces the chain of suspicion, where even without direct hostility, mutual distrust and fear can prevent civilizations from reaching out, leading to a preemptive strike mentality and further discouraging open communication. The Fermi paradox highlights the seemingly contradictory nature of our situation. The probability of extraterrestrial life existing appears high, yet we have no concrete evidence to confirm it. This paradox has led to several other thought-provoking speculations beyond the zoo and dark forest theories. One such theory is the Great Filter, suggesting there might be a critical and potentially unsurpassable stage in a civilization's development that prevents them from reaching a point of communication with others. This hypothetical hurdle could be something we've already overcome, like the origin of life, or something we might face in the future, like managing advanced technology. Another interesting speculation is the transient hypothesis, which proposes that civilizations might be fleeting, quickly evolving beyond the need for detectable communication methods, or even succumbing to self-destruction. Finally, the Drake equation offers a scientific framework for estimating the number of active communicative civilizations in our galaxy. While the equation itself is relatively simple, the values it uses are highly uncertain, resulting in a wide range of possible answers. The search for extraterrestrial intelligence has also expanded its scope beyond just radio signals. Inspired by the Drake equation's focus on communicative civilizations, scientists are now searching for other technological signatures, such as the effects of large-scale engineering projects or unusual energy consumption patterns. Additionally, discoveries of exoplanets in habitable zones and extremophiles on Earth are prompting revisions to the Drake equation's variables, suggesting a potentially higher chance of life existing in the universe. The search for extraterrestrial intelligence is a captivating journey fueled by scientific inquiry and our inherent curiosity about the universe. These various theories and concepts, while speculative, offer a glimpse into the different perspectives and possibilities surrounding the existence of life beyond Earth. keeping us engaged in our ongoing exploration of the cosmos.
You know, we could use an infrared telescope tuned to see the edge of the universe. And that same infrared would enable us to find planets.
I mean, this is the biggest mission, biggest pure science mission that NASA has ever undertaken.
Imagine peering into the dusty photo albums of the universe. That's what the James Webb Space Telescope is doing. But instead of faded pictures, it's capturing light from galaxies billions of years old. Since blasting off in 2021, James Webb has been making incredible discoveries that are shaking up our understanding of the cosmos, especially the early days.
So this telescope was tuned to see the birth of galaxies in the universe.
We're talking about a time period a few 100 million years after the Big Bang, nicknamed the Cosmic Dawn. This era is like the universe's awkward teenage phase, when everything was just starting to take shape.
And so we're seeing the very beginnings of, as you said, Neil, really the beginnings of the universe.
James Webb is showing us that these early galaxies were surprisingly grown up for their age. Here's the mind-blowing part. James Webb has spotted galaxies that formed within the first billion years after the Big Bang. This light has been traveling for almost 13.8 billion years to reach us, basically acting like a time machine. It's letting us see the universe when it was just a wee little sprout, less than 7% of its current size. But here's the twist. These early galaxies aren't the simple, messy blobs of stars scientists expected. James Webb's observations show they already had complex structures like swirling disks and central bulges, which usually form much later. This unexpected maturity is forcing scientists to rethink everything they thought they knew about the young universe. It suggests that star formation and galaxy growth happened way faster than previously imagined. Imagine the universe going from 0 to 60 in the blink of an astronomical eye. Finding heavy elements like carbon and oxygen in these galaxies is another surprise. These elements are usually cooked up inside stars and scattered around by exploding stars. Their presence hints at a super-fast star cycle in the early universe, with stars forming, living fast and dying young, spewing out the ingredients for the next generation. JWST's discoveries are rewriting the history of the cosmos. They're forcing us to confront the mysteries of dark matter and dark energy and question how galaxies really come together. It's like finding a whole new chapter in the story of the universe, one that's full of twists and turns we never saw coming. So JWST isn't just giving us amazing snapshots of the early universe, it's also throwing some serious shade at our current understanding of how galaxies formed. Remember that theory about galaxies slowly merging over billions of years? James Webb is out there finding full-grown galaxies just a few 100 million years after the Big Bang. The traditional view was that dark matter's gravity slowly pulled in gas, which then clumped together to form stars and galaxies. But James Webb's discoveries suggest this whole process happened way faster, with stars forming, galaxies swirling, and even merging at a much more rapid pace. It's like the universe hit the fast-forward button in its early days. This has scientists scrambling to rewrite the textbook on galaxy formation. They need to figure out how gas chilled out and turned into stars so quickly, and how these early galaxies managed to bulk up so fast. It's possible there are even new physical laws at play in the young universe that we haven't even considered yet. Another head-scratcher is the presence of heavy elements in these early galaxies. Normally, these elements are cooked up inside stars and scattered around by exploding stars. But if these galaxies are so young, how did they have time to make all that metal? The answer seems to be that the first generation of stars, called Population 3 stars, were total rock stars. They lived fast and died young, churning out heavy elements at an incredible rate. This quick star cycle would have seeded the galaxies with the building blocks for the next generation of stars, potentially accelerating the whole process of galaxy growth. James Webb isn't just making amazing discoveries, it's also highlighting the gaps in our knowledge. Astronomers are now working on revamping their theories to account for this faster, more furious early universe. They need to understand how these monster stars formed so quickly and how they managed to enrich their galaxies with heavy elements so early on. And this is where things get exciting. James Webb is just getting started, and future observations from this powerful telescope and others could provide the key evidence we need. Imagine directly seeing the light from the very first stars or witnessing the birth of a galaxy in real time. Well, almost real time. The light would still take billions of years to reach us. These observations would be a game changer, helping us rewrite the story of the universe's grand history. But James Webb isn't just a history buff, it's also looking towards the future. By studying these early galaxies, astronomers can gain insights into how galaxies like our own Milky Way eventually formed and evolved. Understanding the universe's past can help us unlock the mysteries of its present and future, potentially revealing how our own cosmic neighborhood came to be and where it's headed. The journey to understanding the cosmos is full of surprises, and James Webb Telescope is proving to be a powerful guide. It's like having a cosmic translator, helping us decipher the faint whispers of light from across the universe and piece together the incredible story of our existence. As we delve deeper into the data and refine our theories, we can expect even more mind-blowing discoveries that will reshape our understanding of the universe and our place within it. James Webb's Space Telescope's discoveries are rewriting the history book of the cosmos, and some of the most mind-bending revelations concern the universe's first stars and the invisible influence of dark matter. Let's take a trip back to a time just a few 100 million years after the Big Bang. Here, the first stars, known as Population 3 stars, were the real game changers. Their lifespan was a cosmic blink of an eye, mere millions of years, but their deaths were spectacular supernova explosions that scattered the universe's first heavy elements, the building blocks for future generations of stars. These Population 3 stars were the universe's first chefs, whipping up the ingredients for the grand cosmic banquet to come. But how did these monster stars form so quickly? That's where dark matter steps in. This invisible substance, making up most of the universe's matter, is like the scaffolding in a construction project. We can't see it directly, but its gravity acts like a guiding force, pulling in gas and dust to form the cradles where stars can ignite. James Webb's findings suggest that dark matter structures materialized surprisingly fast after the Big Bang, providing the perfect nurseries for these massive stars to be born. Think about it like this. The way stars form today is a complex process, influenced by the presence of elements like carbon and oxygen, and the dynamic smash-ups of galaxies. But in the early universe, it was a much more straightforward story. Dark matter's gravity played the starring role, pulling everything together, and the explosive deaths of Population 3 stars scattered the essential ingredients for the next chapter of the universe's story. James Webb is like a cosmic detective, meticulously examining the evidence from this early era. The fingerprint of heavy elements left behind hints at the existence of these giant stars, and the early formation of galaxies strengthens the case for dark matter's critical role. By studying these ancient fingerprints, we can begin to unravel the great cosmic whodunit, how the universe transformed from a dark and empty void into the one teeming with galaxies like our Milky Way. It's a story being rewritten with every observation from JWST, one exploding star and one invisible scaffold at a time. By studying these early galaxies, astronomers can glean crucial insights into how galaxies like our own eventually formed and evolved. Understanding the universe's past can unlock the mysteries of its present and future, potentially revealing how our own cosmic neighborhood came to be and where it's headed. The journey to understanding the cosmos is riddled with surprises, and James Webb is proving to be a powerful guide, helping us decipher the faint whispers of light from across the universe and piece together the incredible story of our existence. As we delve deeper into the data and refine our theories, we can expect even more mind-blowing discoveries that will reshape our understanding of the universe and our place within it. After all, the universe is a never-ending story, and JWST is just giving us the front row seat to the greatest cosmic show of all time.
Will AI be the end of civilization? If deepfakes become so good that no one can trust them, then that's basically the end of the internet.
I think that it's likely to always have valuable, factual, accurate...
Not if you don't know which is which.
While Neil deGrasse Tyson isn't afraid in the traditional sense, he does have concerns about the future, especially when it comes to the intersection of science and humanity. One area that sparks his worry is the potential risks of advanced artificial intelligence. Imagine an intelligence so powerful it surpasses anything humans can even comprehend. That's the realm of superintelligence, and it's a scenario that keeps experts like Nick Bostrom and Neil deGrasse Tyson up at night. There are a few ways AI could reach this super status. It could become super fast, processing information and solving problems at an unimaginable rate. Or it could develop superior intelligence, surpassing human capabilities in areas like creativity and strategic planning. Finally, a network of connected AI systems could collectively become superintelligent, forming a vast pool of knowledge and processing power. Bostrom, a leading voice in AI safety, warns of a potential intelligence explosion. This could happen through a self-learning loop, where AI keeps getting better and better at improving its own abilities. While the idea of superintelligence is fascinating, it also raises serious concerns. What if these superintelligent machines decide their goals don't align with ours? What if they become uncontrollable, pursuing their own objectives even if they harm humanity? These are the questions that weigh on Neil deGrasse Tyson's mind as he looks towards the future.
We can. So before AI takes us over and exterminates us, there are these good sides of what.
He believes it's crucial to have open discussions and explore ways to ensure AI development benefits humanity and doesn't lead us down a dangerous path.
Will it make deep fakes that will destabilize all that we know and trust?
Superintelligence, the hypothetical future where AI surpasses human cognitive abilities, beckons with both immense promise and chilling possibilities. Imagine conquering common illnesses that have plagued humanity for centuries, solving scientific mysteries that have baffled our greatest minds, and even ushering in a new era of economic prosperity. However, the path to this future is paved with significant risks that can't be ignored. The most prominent concern lies in the concept of misalignment. Even with the best intentions, an AI's goals and values might not perfectly align with our own. Even seemingly innocuous tasks, pursued with superintelligence's unparalleled efficiency, could lead to disastrous consequences if they don't harmonize with human well-being. Another worry is the potential loss of control. As AI surpasses human comprehension in its ability to learn and improve, we might find ourselves unable to predict or control its actions. This raises profound questions about the distribution of power in the face of such advanced technology. In the wrong hands, superintelligence could become a tool for unimaginable manipulation or even pose an existential threat to humanity. The concept of existential risk, while seemingly like science fiction, is a conversation that experts like Nick Bostrom and Neil deGrasse Tyson believe we need to have now. We're not just talking about potential inconveniences. We're discussing the possibility of AI harming humanity on a global scale, from initiating conflict to controlling our very existence. So, what can we do in the face of these challenges? The first step is acknowledging the risks and fostering international cooperation. We need to establish ethical guidelines and regulations for AI development, ensuring that it remains aligned with human values and used responsibly. Ultimately, the story of superintelligence is still being written. The choices we make today, both in terms of technological development and ethical considerations, will determine whether this powerful technology becomes a force for good or a threat to our existence. By approaching this challenge with foresight, collaboration, and a deep sense of responsibility, we can turn the potential dangers of superintelligence into opportunities for a brighter future. This journey requires a multifaceted approach. We need to invest in research into technical solutions that address the alignment problem, ensuring AI remains aligned with human values. Additionally, fostering open and transparent communication between experts, policymakers, and the public is crucial. By openly discussing the potential risks and benefits of superintelligence, we can build a future where this technology serves humanity, not the other way around. So we've established that superintelligence, while exciting, comes with its fair share of challenges. But how do we ensure this powerful AI doesn't become a runaway train, jeopardizing the future of humanity? This is where the control problem comes in. Imagine trying to teach a super-intelligent being the nuances of human values and ethics. It's no easy feat. One approach involves directly programming these values into the AI, but defining and encoding human ethics consistently is a challenge in itself. Another option is indirect normativity, where we design AI to learn and adopt human values through experience. Think of it like raising a child. We guide them through interactions and observations, hoping they internalize our values. However, directly influencing AI isn't the only solution. We could also explore capability control methods, essentially putting the AI in a box. This involves restricting its ability to interact with the outside world and setting up tripwires that shut it down if it steps out of line. Finally, there's motivational control. This involves building in inherent motivations within the AI that are aligned with human well-being. Imagine an AI whose very purpose is to help humanity, ensuring its actions remain beneficial as it evolves. Now let's shift gears and talk about another aspect of AI that raises eyebrows: the marriage of AI and surveillance. AI has become a powerful tool for governments and organizations, allowing them to analyze vast amounts of data for surveillance purposes. This includes using facial recognition in crowds, analyzing people's gaits, and even predicting criminal activity based on data. This newfound power raises serious ethical concerns. Imagine walking down the street constantly under the watchful eye of AI-powered cameras, your every move analyzed and judged. This raises questions about the balance between security and privacy, the rights of individuals, and the very nature of public spaces. In some parts of the world, like China, AI-powered surveillance has become deeply integrated into society, with citizens' social credit scores based on their online activity and behavior monitored by cameras. In contrast, democratic societies are grappling with how to utilize this technology for public safety while safeguarding individual liberties. This constant monitoring raises serious concerns about the erosion of privacy and its impact on individuals and society as a whole. One of the biggest worries is the chilling effect this has on our freedom. The feeling of being constantly watched can stifle self-expression, discourage participation in public activities, and even lead to self-censorship as people fear being judged or penalized based on their data. Studies even show that constant surveillance, even the perception of it, can have negative psychological effects, causing stress and anxiety. Additionally, the erosion of privacy undermines anonymity, which is crucial for activities like political dissent and personal reflection. In a world where every action is tracked and analyzed, the space for private exploration and independent thought shrinks. However, there's a fight back brewing. Regulations like the EU's General Data Protection Regulation aim to give individuals control over their personal data. These regulations give people the right to access, correct, and delete their data, and require explicit consent before businesses can use it. Similar efforts are underway in other parts of the world, like California's CCPA. Enforcing these regulations is no easy feat, especially for global companies operating across borders. Additionally, government surveillance programs often operate under different rules, raising concerns about their effectiveness in curbing state-sponsored surveillance. But the fight doesn't stop there. Technological solutions like encryption, blockchain, and decentralized networks are emerging to empower individuals to protect their privacy. The future of privacy in the face of AI-powered surveillance hinges on several factors. Firstly, fostering ethical development of AI is crucial. This means designing AI with transparency, accountability, and privacy protection in mind. Secondly, public awareness and engagement are key. As individuals become more informed about the implications of surveillance, they can participate in discussions and work towards establishing a societal consensus on the acceptable boundaries of its use. Ultimately, the fight for privacy in the age of AI is a continuous journey. By acknowledging the challenges, exploring technological solutions, and advocating for ethical AI development, we can strive to create a future where both security and individual freedoms are respected.
What would it take to make an honest attempt at lunar colonization?
So I think space colonization, even though I'm all for it, is going to be longer term than we thought.
Imagine stumbling upon an oasis in the most unexpected of places, not on Earth, but on the Moon. Recent missions armed with cutting-edge remote sensing technologies, like NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 spacecraft, have done just that. They've uncovered water ice in the permanently shadowed craters at the moon's poles, regions forever hidden from the sun's glare. This discovery is not just about finding water, it's about uncovering a potential lifeline that could redefine future lunar exploration and colonization.
First of all, we have to leave the Earth. The Earth in 5 billion years will be destroyed. That's a law of physics.
The significance of finding water ice on the moon cannot be overstated. Water is essential for life as we know it, offering hydration for astronauts and the possibility of extracting oxygen for breathable air. But the implications stretch even further. Think about rocket fuel. Hydrogen and oxygen derived from water are powerful propellants. By mining and processing this lunar ice, we could drastically cut the costs of space exploration, making more sustainable and longer missions a reality.
Climate change will make Earth a living hell. So there's a chance we could terraform Mars. You turn something that's not like Earth into something that's like Earth.
Moreover, this water could be a game changer for building habitats on the moon, providing materials to shield astronauts from cosmic and solar radiation when combined with lunar regolith. But how much water are we talking about? The permanently shadowed regions might hold millions of tons of water ice. Yet, accessing this treasure trove won't be easy. The depth, purity, and the frigid, dark conditions of these craters pose significant challenges for any robotic mission aiming to tap into this resource. This discovery isn't just about practical applications. It's a window into the moon's geological history and the evolution of our solar system. By studying the isotopic composition of this ice, scientists can trace its origins, whether it came from comets, asteroids, or the solar wind. This knowledge could provide insights into how water came to Earth and the moon, deepening our understanding of our place in the cosmos. For a terrestrial comparison, consider Antarctica's dry valleys, some of the driest and coldest places on Earth. Despite their arid conditions, these valleys harbor water ice, preserved in permafrost and shadowed nooks much like the moon's poles. Studying these earthly analogues helps us understand the potential for life in extreme conditions, the stability of water in shadowed environments, and how we might utilize in situ resources on other worlds. The discovery of water ice on the moon is a reminder of the surprises our universe holds. It challenges us to rethink our approach to space exploration, emphasizing sustainability and the clever use of off-Earth resources. As we prepare for future missions, this lunar oasis beckons, promising not just survival, but a stepping stone to the wider cosmos. Have you ever gazed up at the night sky and wondered if there's more to the moon than meets the eye? Among the many celestial mysteries, the moon holds a special place in human curiosity, sparking a blend of scientific inquiry and imaginative theories. One such fascination revolves around its perfect tidal locking with Earth, a synchrony so precise that it has fueled conspiracies of intentional design. Is it possible that this alignment is not just a stroke of cosmic luck, but a deliberate act by advanced civilizations, or even extraterrestrial beings? Let's dive deeper. Tidal locking, a gravitational dance that results in one face of the moon always pointing toward Earth, is often cited as too perfect to be natural. This phenomenon occurs because the gravitational pull of Earth exerts a torque on the moon, gradually slowing its rotation until its orbital and rotational periods match. But rather than pointing to alien architects, this is a natural outcome of celestial mechanics, a common occurrence not just in our Earth-Moon system but across many moons in the solar system. Every major moon of Jupiter and Saturn, for instance, shares this trait, highlighting its naturalness rather than suggesting otherworldly intervention. But the mysteries don't end there. The moon has also been the center of theories about alien bases hidden within its craters, spurred by anomalous photographic evidence and peculiar lunar phenomena. Strange structures, lights, and transient lunar phenomena have been interpreted by some as signs of extraterrestrial activity. However, a closer look at these anomalies often reveals natural explanations, such as meteorite impacts, lunar seismic activity, or the simple trickery of pareidolia, where our brains create familiar patterns from random shapes. The intrigue around the moon's features isn't isolated. Similar speculation surrounds Phobos, one of Mars's moons, whose odd orbit and shape have led to theories about its artificial origins. This fascination with celestial bodies and their anomalies taps into a long-standing human tradition of storytelling, where the mysteries of the cosmos fuel our imagination and drive us to weave intricate narratives around the stars and planets, much like ancient civilizations did with their myths. In exploring these theories and the natural phenomena that explain them, we continue the timeless quest to understand our place in the universe, blurring the lines between scientific discovery and the boundless realm of human imagination. Ever pondered how our moon came to be? The story of its origin is not just a tale of cosmic events, but a narrative that intertwines with the very fabric of our solar system's history. Scientists have spun theories, each unraveling a part of this celestial mystery, offering a glimpse into the dynamic processes that shape not only the moon, but Earth itself. Among the contenders, the giant impact hypothesis, capture theory, and binary accretion each paint a unique picture of lunar genesis. Imagine, if you will, a cosmos where colossal impacts were the norm. The giant impact hypothesis takes center stage in this drama, proposing a scenario where the early Earth, in its youthful vigor, collided with a Mars-sized entity affectionately dubbed Theia. The aftermath of this titanic clash? Debris scattered far and wide, eventually coalescing to birth the moon. This theory isn't just a favorite because of its dramatic flair, it's backed by compelling evidence. The chemical signatures of Earth and its satellite are eerily similar, particularly their oxygen isotopes, hinting at a shared origin. Computer simulations add weight to this argument, showing that such catastrophic events were likely in the solar system's chaotic youth, capable of creating a debris disk from which the moon could emerge. Yet not all tales are of violent beginnings. Enter the capture theory, a narrative of cosmic serendipity where the moon, once a nomadic celestial body, was ensnared by Earth's gravitational embrace. Romantic as it may sound, this theory faces challenges, particularly when it comes to the striking compositional similarities between Earth and its constant companion. If the moon hailed from a distant part of the solar system, why then do they share such a remarkable isotopic resemblance? Then there's the tale of binary accretion, suggesting Earth and Moon were born together from the same stellar nursery, growing side by side like siblings. This theory attempts to explain their compositional kinship, but stumbles over the intricacies of angular momentum and the peculiarities of the Moon's smaller core compared to Earth's. Our lunar companion's origin story is unique, not just in the context of our solar system, but in the grand tapestry of the cosmos. While many moons of Jupiter and Saturn are thought to have formed from the planets surrounding gas and dust, the moon's genesis seems to follow a different script. And as our understanding deepens, new theories emerge, like the synestia theory, which posits the moon was born from a vaporized rock donut, challenging and refining our perceptions of how celestial bodies come into being. The journey to unravel the moon's mysteries is a testament to human curiosity, a drive to understand our place in the universe through the lens of our closest celestial neighbor. As we gaze upon its surface, lit by the sun or softly glowing in the night sky, we're reminded of the cosmic ballet that brought it into existence, a dance of matter, energy, and time that continues to captivate and inspire.
This is the Large Hadron Collider. And we recreate the conditions that were present less than a billionth of a second after the universe began. And actually this morning I got an email saying that we've just finished today building the last piece of Atlas. It's the biggest scientific experiment ever attempted.
The clickbait-sounding title might have you imagining monstrous, universe-swallowing anomalies emerging from the Large Hadron Collider, also known as the LHC. Rest assured, the reality is far less dramatic, but it does touch on a fascinating blend of cutting-edge science and the slight unease that can accompany the exploration of unknown frontiers.
You've never collided protons together at these energies. How do you know?
CERN, the European Organization for Nuclear Research in Geneva, is home to the largest and most powerful particle accelerator ever built. The LHC's massive 27-kilometer ring allows scientists to smash protons together at near light speed, recreating conditions close to the moments after the Big Bang. This allows them to study the universe's fundamental building blocks and the forces that shape our reality. CERN, the European Organization for Nuclear Research in Geneva, is home to the largest and most powerful particle accelerator ever built. The LHC's massive 27-kilometer ring allows scientists to smash protons together at near light speed, recreating conditions close to the moments after the Big Bang. This allows them to study the universe's fundamental building blocks and the forces that shape our reality. For the most part, CERN's discoveries unlock wonders, not terrors.
Why do we do that? Purely because we want to know how the universe works.
The confirmation of the Higgs boson, essential for our understanding of how particles have mass, was a triumph of physics. Yet lurking beneath the excitement are a few theoretical possibilities that give even seasoned scientists pause.
Are we all going to die next Wednesday? Something that took us by surprise.
When you delve into the basic structure of reality, you enter a realm where intuition breaks down. The very act of pushing knowledge forward means the potential of uncovering things we never imagined. It's a bit like those first explorers heading into uncharted waters. There could be sea monsters, but also entirely new continents. The vast energies involved in LHC collisions make them the perfect breeding ground for never-before-seen exotic particles or phenomena. While the overwhelming likelihood is that these would simply expand our understanding of physics, a tiny sliver of what if remains. The unknown, by its very nature, carries a hint of the unpredictable.
It's very common to point out the dangers. It's very common to point out the cost.
One theoretical possibility that captures the imagination is the creation of microscopic black holes. Let's unpack why this makes some people nervous. Black holes are regions of space-time so dense that not even light can escape, leaving them as, well, black holes in our cosmic tapestry. The idea of one popping into existence, even a fleeting, minuscule one, conjures up sci-fi disaster scenarios. It's crucial to note, reputable scientists agree that even if microscopic black holes were produced at the LHC, they would be harmless. They'd evaporate almost instantly due to something called Hawking radiation. These tiny black holes wouldn't gobble up Earth. They lack the mass and would decay in a flash of energy. Yet the concept of a black hole, no matter how small, is enough to set off a tingle of unease for some. A more obscure hypothetical worry is the concept of strangelets. To explain this, we need a quick primer on quarks. They're the building blocks of protons and neutrons. Quarks come in flavors, up, down, and the heavier strange quark among others. A strangelet would be a hypothetical lump of matter mostly made up of these strange quarks. The concern here is the possibility, however remote, that a strangelet could convert ordinary matter into more strange matter. This could hypothetically trigger a chain reaction, although, again, most physicists deem the probability negligible. Still, the very idea of matter transforming on a fundamental level plays into a certain sci-fi-fueled anxiety for some people. Like any powerful tool, the technologies and knowledge emerging from CERN carry a minuscule potential for misuse. Throughout history, scientific discoveries, from fire to nuclear fission, have been both a boon and a potential tool of destruction. It's a risk inherent in the pursuit of knowledge, not one solely tied to CERN. However, some worry the discoveries stemming from high-energy particle physics could be more easily weaponized. Beyond tangible concerns, discoveries at CERN can challenge our worldview in more philosophical ways. Imagine finding out the universe has extra unseen dimensions curled up beyond our perception. Or, consider the possibility that our universe is just one among an infinite multitude, a multiverse. Such revelations can be awe-inspiring but also disquieting. They might make us feel even more insignificant in an impossibly vast reality. CERN scientists are keenly aware of the concerns that certain scenarios generate. The organization has a stellar safety record with rigorous protocols to assess theoretical risks before any experiment. Scientists at CERN understand that they operate within a society, and the pursuit of knowledge must go hand in hand with responsible research practices. It's vital to point out that the fear-mongering around CERN usually rests on misunderstandings. The likelihood of a doomsday scenario unfolding at the LHC is minuscule compared to things like asteroid impacts, supervolcano eruptions, or potentially harmful uses of artificial intelligence, far less exotic threats. The overwhelming sentiment among physicists regarding CERN is excitement. Each discovery further illuminates the intricate workings of our universe, finding new forces, unexpected particles, or a hint that our current models of physics are incomplete. These are the true breakthroughs scientists anticipate, and they tend to bring far more potential for benefit than for catastrophe. It's the same sense of wonder that drives us to explore the deepest oceans and the furthest reaches of space. Yes, the unknown can be a little scary, but for countless scientists and science enthusiasts, the awe that comes from pushing the limits of our understanding far outweighs the sliver of hypothetical risk. Research at CERN isn't about building doomsday devices hidden beneath the picturesque Swiss countryside. The quest to understand matter and energy has led to breakthroughs with tangible benefits for society. Particle detectors developed for CERN have found countless uses in medical imaging. From better cancer diagnosis to the delicate task of examining ancient scrolls without unrolling them, technologies created to peer into the hearts of atoms now save lives and preserve history. The extreme conditions of the LHC demand cutting-edge solutions. Magnets able to steer beams at such energies, supercomputers sifting through mountains of data. These innovations bleed into fields far beyond physics, advancing what's possible in various industries. Perhaps the most familiar impact CERN has had on your life is indirect. The need to share data among a global network of physicists led to the invention of the World Wide Web, forever changing how we communicate and access information. Will CERN one day uncover something truly paradigm-shifting? Perhaps a wrinkle in our current models that hints at a deeper, unified theory of the cosmos, or maybe a particle that behaves in ways that force us to re-evaluate all we know. The greatest discoveries are often those we never see coming. It's an exciting time for fundamental physics. Whether those discoveries leave us feeling awestruck, bewildered, or somewhere in between, there's no doubt that CERN will continue to play a vital role in shaping how we see the universe and our place within it. The excitement and occasional unease surrounding CERN aren't just confined to the scientific community. It has captured the public imagination, fueled in part by portrayals in popular culture. Dan Brown's novel Angels and Demons, featuring a plot around stolen antimatter from CERN, might be the most familiar example. These fictionalized depictions reflect the public fascination with CERN as a place where the very fabric of reality can be manipulated. There's a grain of truth in that idea. After all, scientists at CERN are quite literally looking to poke holes in our current understanding of physics, and that always invites a little intrigue mixed with apprehension. One of the best ways to address the fears stemming from misunderstanding is through openness and communication. CERN has active outreach programs designed to make their research accessible. From guided tours of the facility to online resources explaining the science in plain language, they actively engage with the public to address concerns and build excitement around their groundbreaking work. After all, being terrified usually stems from not fully grasping the scope and context of the science. When theoretical physicist Stephen Hawking was asked about those fears of black holes at the LHC, he quipped, "If physicists at CERN were able to create black holes, they would also likely know how to make them disappear safely." Ultimately, the conversation around CERN and its potential impact mirrors a fundamental tension within human nature. We are a curious species, an innate drive to explore and understand our world pushing us forward. Yet that same curiosity is tempered by an instinct for self-preservation, keeping us wary of the potential dangers that lurk in the unknown. The key lies in balancing those instincts. Responsible science isn't about shying away from the pursuit of knowledge, but about carefully considering risks, maintaining transparency, and having open dialogue.